Okay, so here we are. Here we are. Um, let's see, we're live, right? I wanted to take a look at something. Um, Again, and forgive me, my thoughts are all over the place. Um, Praise God, man. Praise God. That's all I could say. That's all I have to say. So, what I would like to do is take a look at the problem we were looking at the past few days, revisit it, and just look at it. Just keep thinking about it, because there are some ideas I've had to improve make an improved solution, and yeah, I guess there's nothing to it but to just keep going, keep trying. So I'm gonna try that. Let me give that a shot. Um, let's do this. Let's do this. So, medium, and oh, right here. Okay. Yeah, so I went over the problem the other day. I'm not gonna go over it again. I think we've gone over it a few times. Going to get right into the possible way to improve this solution. So one of the things we were thinking about doing was, actually, let me do this. Yeah, it's fine. Okay. Pull up the notes from the other day. I had this data structure here that we were tinkering with, this tree structure. So my thinking is maybe I should look into how trees are self-balanced in general, and not spend too much time trying to think of a way to do it myself. That's kind of what I'm thinking. Although it doesn't seem too hard to do it myself. Like if we just took a tree, it doesn't seem that difficult. Like we just take an example, right? Tree like this, and we want to insert a node here, right? At this index, this is 0, 1, 2. This would be 3, 4. So let's do it this way. Let's make 2 copies. Just see how long it takes. Let's spend like an hour maybe trying to think about for ourselves, just for myself, see how far I get on my own. And then I'll look into like how other trees are balanced, or self-balancing. 1, 2, 3, 4, 5, 6. Okay. So what we want to do is insert a node at position 3. So 0, 1. Actually, one more copy, I think. This would be 0, 1, 2, 3. Oh, we just did that, right? Yeah, we did. I don't know why I want to do it that way. I want to do this, actually. I just want to keep a untouched copy over there. That way we can always copy that whenever we want, manipulate it. Okay, we want to add a node here. This is what I'm trying to get at here. I want to add a node here at 4, right? At index 0, 1, 2, 3. We want 3 and all these other values to the right. These nodes to the right all increase in their index. So the new setup would look like this: 4, 5, 6, 7. Now the question is, technically this would still be balanced. This is fine. The difference between the height, the maximum depth, and the maximum depth minus 1. Every leaf has to be either at the maximum depth or the maximum depth minus 1. That's what makes it balanced. So sort of an equivalent condition for being balanced. So technically this isn't really an issue. It doesn't need to be rebalanced quite yet. But let's say we insert the node, and I think we were talking about before, there's a way to insert this node if we just keep track of how many nodes, basically the size of each subtree. If each parent node keeps track of that information, then it's relatively easy to figure out where we could put our new node. Excuse me, the problem with that before we were describing, if we don't do any rebalancing of any kind, is we end up in a position where our tree is basically just like it looks like just a list, sort of from left to right. You could have the list split in half, but still the traversal of that list, it still would be half the list on one end, half on the other, and you'd have linear time to traverse the tree when you perform your operations, so you would not get the speed boost that we're trying to achieve. So super important for us to keep the tree balanced. How are we going to achieve that, though, is the question. So what we want to do is we may not necessarily do anything in this situation. I don't know. I don't actually know. I don't know if we should. I don't know where the fourth node should be, if that makes sense. So let's say we do try to balance this somehow. I want to say what we should end up with is actually a node here, right? Yeah, I didn't draw the connections. And so then we would have 0, 1, 2, 3, 4, 5, 6, 7. If we do it this way, where every rebalance basically shifts to what's called a complete tree, where not only is it, or not complete, I want to say, is it complete? Hold on, let me check something. Complete binary tree. Oops. There's a difference between full and complete. Binary, let's try program. Program is. What is this? I don't like to use the different tutorials and things online. Complete, all the levels are completely filled. Full binary tree, not a complete binary tree. Full binary tree. Complete binary tree. Wait, what? Hold on. Complete, where's full? Wait, full. It's a special type binary tree in which every parent node, internal node has either 2 or no. Excuse me. What happened? Where did it go? I realize that's the most attractive thing you've ever seen. Just a giant glob of saliva flying out. Being that this is recorded, you could actually pause the video and rewind it to see that in slow motion if you wanted to. I know it went somewhere, but I can't see it, so I'm concerned. I wanted to wipe it away because it was pretty gross, but I think it's just somewhere in the depths of my keyboard now, never to be found. Or it's on this napkin that I keep in front of me. I don't see it on the napkin though. Gross. Anyway, sorry about that. Oh, so full means okay, yeah, I thought full is not what we're looking for. So full is 2 or no children. Okay. Proper binary tree. Okay, yeah. So, no, we're not looking for a full tree. Whoa. We're looking for, all right, what's complete mean? Complete binary tree is a binary tree in which all the levels are completely filled except possibly the lowest one, which is filled from the left. Okay, so we want complete binary trees. Just like a full binary tree, but with 2 major differences. All the leaf elements must lean towards the left. The last leaf element might have a right sibling, i.e. a complete binary tree doesn't have to be a full binary tree. Yeah. So this is not full and it's not complete. Okay, right, because this node would have to be on the left side for it to be complete. Okay, understood. Yeah, I was right. Complete. That's what we're looking for. Yeah. All right, my memory serving me well here. Anyway, so yeah, basically, if we ensure that our binary tree is always complete after each, we rebalance each step to ensure that it's complete, then our tree would necessarily be excuse me, would necessarily be balanced at all steps. Fair enough, but easier said than done, isn't it? How exactly do we intend to achieve that? That's the question. That is the question. That is the question. So, I don't know. How would you rebalance this? So, these are all the same nodes. Basically, what happened? This is why I wanted to copy this, because this is useful to. So basically, the red movement is going to be where the nodes went. So this 0 node went here. This 0 went there. This 1 went here. This 2 went here. This 3 came down, which was previously at the top. Oh no, yeah, the 3 was previously at the top. Actually, well, it wasn't. No. The 3 is what we just added, right? That got shifted to 0, 1, 2, 3. It was over here. So we did have a node here. And this got shifted up here. And then 4 well, actually, I don't know if we do the rebalancing and the insertion at the same time. I want to say if we go from rebalancing and then insert and then rebalance, then I guess we would go from this chart to where we are now. So 3 comes up. Where does 4 go? 4, that's all the same, actually, from that point on. These are all in the same spots, right? So now, the thing about this, though, is all of these nodes got shifted around. Now, what was this substructure got shifted around from 0, 1, 2, 3. It was just this 0, 1, 2, 3, like this. Excuse me. 0, 1, 2, 3. And then this ended up moving to 0, 1. Like that didn't change, but the 2 became apparent. And the 3 became a child of 2. So you have this 2, 1, 3, 0. So that from a little bit disorienting. This ends up here. Okay. So, oh, there's something we're missing here, which is like so. Okay. So basically we went from this tree, 0, 1, 2, 3, to this tree on the left side. And the thing that's interesting about it is we really did only change one thing. We just rotated this 2 up here. That's kind of all we did. It's kind of all we did. This 2 went up. Let's get rid of these. Otherwise, everything else stayed the same, right? So, yeah, this, let's just say this 2 went up to become the parent. Right, we'll do it this way. Kind of represent these changes. And I think that's kind of it. Actually, 2 is still the parent. Like we only really changed one thing on this diagram here. And now we have 0, 1, 2, 3 here. Right? Okay, something like this. Anyway, so yeah, that's all well and good. However, it's sort of similar to one of the operations we were looking at before. That's fine, I guess. What happens if we add another node, right? Add same thing again, same position 3 again. I don't know, I'm kind of thinking like what are all the different possible what do they call it? Possible different operations and transitions between trees. Because this actually is kind of I want to say there is some kind of like recursive structure here or iterative structure where basically, since this is a subtree, you're actually just rebalancing a certain subtree, right? And there's only 4 nodes here to look at. And really in every case, I guess, if the tree is complete to begin with, then there's only so many things that can happen with your rebalancing. I want to say something like that. I actually want to say like you could probably break down every rebalancing into a case where there's 4 nodes involved. And then from there, things get more interesting, if that makes sense. Yeah, ultimately, all you're really looking to do is just push the nodes to the left. That's kind of it. That's really what the rebalancing is. It's just moving your connections in such a way that your tree is always complete, right? Maintaining that condition. It sounds easy enough, but is it? Is it? All right, let's try some more examples. Let's see if we can come up with more things. See if we did this again, right? So we have this now, this tree. Let me do it this way. Let's try adding like a bunch of nodes a few times. I'm gonna sneeze. All right, so, oh boy. Oh, okay. All right. You know what we can do? We can use this for our nodes. And so this is our tree. It's kind of a wonky looking tree. I kind of prefer doing it the other way, but why not? Do it this way. So 0, 1, 2, 3, and we insert 4 here. Four, 5, 6, 7, 8. Okay, so sorry, forgive me. Whoops. All right. Anyway, what's that doing? So. 0, 1, 2, 3, 4, 5, 6, 7, 8, right? I want to rebalance this again. Basically, shift this node here. No, it's not that this node is going to go over there. We're going to shift the tree in such a way that this node goes up and one node comes down. That's basically the idea. It should, in theory, be a logarithmic number of maneuvers where we're going to swap a logarithmic number of nodes upwards, or yeah, move their positions upwards, and then also move a logarithmic number of nodes downwards. Excuse me, that's my thinking, that there's two paths basically to get this node, to get a replacement over here and this node gone, that there would be at most a logarithmic number of steps upwards and then another logarithmic number of steps downwards. That's my assumption, that's my thinking, that's where I'm going with all this. That's why I think this is a viable approach to keep the tree balanced, to keep balancing the tree. What we would want to do probably is take our, we have 3 circles here, right? 2 circles here. Okay. All right. All right. Forgive me. Forgive me. So, 1, 0, 1, 2, 3, 4, 5, 6, 7, 8. All right. We want to. I think we want to push this 1 here. Yeah. And we'll say 1 goes here, 2 goes here. We get this connection between 2 and 0. So there's a swap that happens here, I guess. 3 comes up, 4 comes up, right? And so we end up with, and we don't need to touch this other subtree at all. Actually, it doesn't even matter, you could just flat out. Yeah, so it looks like this. All right, and again, yeah, this is logarithmic number of maneuvers. And this right child becomes where this, so it actually, yeah, I guess there's this common parent, and it really, like, I guess it's really just this node, this index, where you're going to place this node. Not really index, but this position that you're going to place into. What you want to do is fill that spot with what would be the parent. So the parent of that moves in that spot. The parent of that node then what that just, the subtree, the left subtree for that node becomes the left subtree of that parent node, right? This parent node, the right subtree becomes that particular node, and you want to keep a pointer to the right subtree, and then this right subtree, actually you would continue down the path to the node that you were interested in. So I guess both of these spots, these are basically going to shift one into the other, but there's a path up to a mutual parent where basically everything is going to shift from right to left over that path. Yeah, that's logarithmic. I mean, if you could code that correctly, then you're in business. But the question is, like, how do you even process that exactly? I don't know. I want to say there's probably some way to do it recursively, I guess. So let's add. Well, if we do more examples, I think we'll get a better sense. So let's try that. Oh, run out of space. Also, I think the stream kind of flickers, pauses, blanks out a bit each time we save this document, which is kind of interesting. Now we insert something to the right again. Let's say we insert something over here. Let's say this is index 3, 4, 5, 6. Then that makes these indices update to different values. We're looking for is, yeah, that's correct. 5, 6, 7, 8, 9, right? So we place 6 there, and then we want to make sure this is complete, so we rebalance, and we say what's going to happen. So there's this node, and this node, and the parents to this node, all of these guys. The parents to this node are these guys. Literally, like algorithms, you can describe them in English, how you might do it by hand, like in English, and then you can translate that to code. That's typically how you might program something, like how you write a new algorithm. That's how I usually do it. And then if you realize that this translates to like a general case, then you're in good shape. You can sort of always do things that way. So okay, so yeah, so first I guess we're gonna find the parent paths, and then they meet somewhere, right? And then we're gonna take this first parent path, we're gonna reverse the other parent path, the other direction. And what we want to do is actually shift all of our nodes in that direction. So push this node here, push that node there, push that node there, push that node there, push that node there, and push that node there. And we're going to perform all these swaps on the nodes. And some of these nodes are going to be swapping with their parents, and some of them are swapping with their children, which is significant. Yeah. The reason we probably want to get these two parent paths first and then reverse one of the parent paths is we definitely want to, we don't want to lose this path, this like order of operations. We don't want to lose it, if that makes sense. But yeah, we could pretty much create like a linked list of pointers of the nodes to get an idea of what's going to be swapping with what. And so I guess you actually start at where do you begin? I don't know. I don't actually know how to do this. Let's say, yeah, okay, we have this path now. All right, fine. We have these two paths. Now, how do we perform this operation? How do we do this? What we want to do is which, by the way, we're also assuming a couple things here. One thing we're assuming is that the node that you just added, like if we wanted to add a node to the 0 index, I guess one of the assumptions we're making is that the node is going to be to the right of that's confusing. Yeah, it doesn't matter that much. That's still fine. It's still a logarithmic number of steps in asymptotic time complexity. I guess what I'm saying is that there could be a node over here from this structure. Like it could actually be any of these leaves could be a node that we're trying to operate on. But even if it's one of these leaves, it's still the same operation. We're still going to try to get a node here and move the node, move this node away up, and move a node here in another part of the tree. So it's the same idea. So even if it doesn't matter where we put the node, if we follow this path correctly, it should work with still logarithmic time in all cases. So that's fine. But then the question becomes, how do we actually perform this? It's like definitely easier said than done, isn't it? So this node becomes a child of this node. It was always a child. But now we don't know if it's a left child or a right child. Actually, I guess it actually probably makes more sense to pull these down and make the adjustments as you go. That's kind of confusing, isn't it? I don't know. I don't actually know how to do this. So, because for this node to come up here, it's already a left child, so it actually wouldn't change. But this node would need to become the right child of this node, and it's a left child at the moment. So that kind of matters. So this node has to become a... Now the question is also like, how do we keep track of all that information? Because naturally things, once you change directions over here, now you have things being children that need to be parents, basically. So the change that this node has to make is this 7 has to be the, this 7, what has to change is this right subtree of its parent has to become the right subtree of 7. And that should be fine, right? Because we know this is, well, we know that actually the right subtree isn't always available or open. But I guess just in this case, it happens to work out where this 9 is going to now be a right subtree of 7. And then 7 was the left subtree of 8. Now that becomes the right subtree of 8 because 8 is going to become the root node. So 7 becomes the right subtree of 8. 8 becomes the root node, which means that 5 is now a left subtree of 8. So let me move all of these nodes into their new positions. What you had and what you now have. We'll put the new nodes, what their indices were, we'll put that in red. So hopefully that makes some sense. So 6 is also, yeah, there's also one more node here. All right. Oops, I don't want that. Okay. So, and forgive me for that blip you see from time to time, right? When I save. Yeah, I can see it's definitely causes the stream to lag a bit. It's probably because this is a lot of space. Probably don't need all that space. Might want to start a new. It's okay. It's fine. We'll just lag when we save. Just don't save it too often, I guess. All right. So this 6 moves up here. This 7 moves up here. Let me erase this 8. This is actually 9. Still the 9. And this 8 becomes the new root node. The left subtree becomes this 5. The 5, its right subtree is now this 3, which was the left subtree. This 3, its right subtree is 4. Oh, excuse me. No, 4 becomes the left. The 4 becomes the left subtree of 3. Okay. Now the question is, we've got all these. Actually, we don't want to do. I'm probably gonna start a new. That's a lot. Probably gonna go ahead and start a new. I don't know if this is. Can I do this? Can I do it that way? No, I can't. Hold on. Let me. I don't want to do this. Kind of resize it to like 3/4 or something. %. Oh. Let's do 75% of that. Does that just make it bigger? I don't know. Where is the? What happened? What did I do? Oh. Let me see. Do it a couple more times. 1, 2, 3. All right, that's fine. We can. Yeah, it's still gonna take a while to save. We probably should just start a new one. Never mind. Anyway. Yeah, we'll just start a new one. Okay, that's fine. Before we do that, let's analyze this a little bit more. So, considering I save it so often, it's gonna be so aggravating for people watching. All right, so 0, 1, 2, yeah. So here's where everything moved, right? But the problem that I think I'm gonna have is like, it's not obvious what the movements should be, I guess, if that makes sense. sure, it's logarithmic time, but like, what gets swapped with what? Because you have a few different options. You have a left child or a right child becomes a parent, and then the parent's children become the children of the left child or the right child. So in each case, we'll go through it one by one. So the 6, it's still a child of 7, but it actually became the left child. It was always the left child of 7, so it didn't actually change. The children of 8, though, the right child of 8 became a right child of 7. And then for 8, the left child that was 7 is now a right child. And 8's parent, which was 5, now the left child becomes 5, right? So 8's left child 7 moved to the right, and the parent came down, right? So parent came down to be the left child, 7 moved to the right to become the right child for 8, which is pretty interesting. For 5, there's no parent for 5. There's a left child and a right child. The right child became its parent, and 5 became a parent to its left child's left subtree became its left subtree, and the left child became its right subtree, right? And then for 3, its parent stayed the same. The right child stayed the right child. Oh no, excuse me. The right child for 3 became the left child, which was 4, and there was no. And there was a left child for 3, but the left child for 3 got absorbed by 5. So that's not at all obvious, like how to, I guess, systematically perform those operations, right? In all cases, that's not obvious at all how to do that. Certainly, there's a way. But who knows? Who knows what you're supposed to do? How you're supposed to do this exactly? It's not enough just to find the path that you're supposed to shift through. I guess you kind of need to know the relationship between the nodes. Like, is the node you're about to swap with a left child, a right child, or a parent? And you do different things depending on those different situations. Actually, I think you break down the parent situation into 2 different cases as well, because the node could be a parent, but you could be the left child of the parent, or the node could be here the node is a parent and it's a left child, but here the node's a parent and you're a right child, right? Excuse me. And if you're a left child, it seems that, you might stay left child. And then that next node, that parent, say, okay, the next node's a parent and you're a left child, but actually you become a right child. Why would that be? So it seems like there's more to it than just a simple, like, what's the relationship between each of these nodes. It seems like there's like a greater picture involved. Because doing this by eye, visually, I know what to do. But to encode that information, it's not obvious. Like, it may not actually be that simple to do this procedure as described. I want to say, again, probably if I read more about self-balancing trees, I'll probably get a better sense. Let me like lay down for a few minutes and just kind of ponder this. But I think 6, yeah, 6 moving upwards, 7 moving up where the parent was, takes the children of 8, 8. So 7 being a left child, now the right subtree of its parent becomes its right subtree. Certainly that makes sense. That'll be true in all these cases. However, what is interesting is where does, so 7 stays, so 7 doesn't stay a left child of 8. So I think if you have a right child, so if the parent has a right child, then this node would become that right child becomes a right child of that node, and this node becomes a left child of this parent. Which it was originally. So how do I know that this is? How do I know that 7 is supposed to be a right child or a left child of 8? You would have to know what 8's relationship is. That's why. That's how you know. Okay, so this child 6 is replacing 7, which is a left child of 8. Or yeah, it's moving to where 7 was, which is the left child of 8. So it's going to stay a left child of 7 because 7 is a left child of 8. 7, on the other hand, is going to move where 8 was, but 8 is a right child of 5. So 7 is actually going to become a right child of 8. And 9 also happens to become the right child of 7. And then 8's relationship with 5 is 5 doesn't have any parents. So actually you would look at the next node, which is the left. So 5 is actually a parent to this left subtree. So 5 is going to be to 8 what 3 was to 5. Ah, that's the way to do it. Okay, that makes sense. That makes sense. That's, I don't know, it's like it's kind of hard sometimes to like understand what you're looking at, what you're dealing with. But yeah, you want to know, basically each node is going to have the same relationship that the previous nodes had, until you get to this point where this node is empty, right? We're at the end of the list where there is nothing. That's where it gets interesting, or where things get a little bit different. So right, so you're going to mirror all the previous nodes' relationships. So you only have to go one node ahead in each case, which is awesome. So 8, 5, and 3. 8's going to be where 5 was. 8 is going to have, so 3 is the left child of 5. That means that 5 is going to become the left child of 8. And we had already shown that 7 is actually going to be the right child of 8. So 7 becomes the right child of 8. 9 had already been made the right child of 7. 8, so 5 becomes the left child of 8. And 3's relationship to, so 3's relationship to 5 now. 5 is the left child of 8. What happens to 3 is, actually no, yeah, what happens to 5 now, so that's what happens to 8. 5 is left child of 8. What happens to 5 depends on 3 and 4. 5 is going to replace 3, so 3 becomes the right child of 5. Right child of 5. And the left child of, since 5 is going to replace 3, the left child of 3 becomes the left child of 5. And why is that? Yeah, that's another thing that's not so obvious. It somewhat makes sense of like how these nodes connect to each other, but what about their children, right? The children that are being moved around. Since 5 is going to replace 3, and 3 is related to 4 So 3 is going to become by the right child. So the right child of 5 is going to be 3. And again, 5 is replacing 3. So the left child of 3 basically would stay the same, becomes the left child of 5. That's what you want, how you want to think about it. So the things that don't get modified, those are going to be changed for that node. So there's 3 different pointers to pay attention to. There's the parent node, there's the parent pointer, there's the left child, right child, and the parent. So those 3 different pointers, you got to modify them correctly. So 5 becoming 3, the left child of 3 should be the left child of 5. The right child of, we already know the parent of 5 is going to be 8, because that's where we came from. So we know the parent of 5. We know the left child of 5 is going to be the left child. So we do it this way. So we know the parent of 5 is 8, because we determined that already, predetermined. The right child of 5 must be 3, because the next node in the list is the right child of 3. So the right child is 3, and that means what's left over is the left child of 3, which becomes the left child of 5. So that's how you figure that out step by step, which one's which. And then similarly for 3, when 3 is being moved here, the right child, so in our list, we want, our target is the left child of 4. So 3 is going to become 4. So the left child of the target, that is where our next node is going to be. So our next node 4 is going to become the left child of 3. We already moved away the left child of 3 to 5, right? The parent for 3 we already know is 5. So that means the right child of 4 becomes the right child of 3. So and that's actually the null node. So now 4 becomes the left child of 3. Right child of 3 becomes null pointer. 3 gets moved down here. 4 is now the left child of 3, and actually at that point we're in the correct position. The tricky thing is we just need to know if this pointer that we're interested in is the left child or the right child of this node. That's kind of just the one piece I think we're missing, is this target index, if that's the left child or the right child, which we can check the relationships between these things by just checking, like we check the relationships of these things by kind of checking the address of the node pointer, like checking the node pointers against each other to figure out if this is the parent or the left child, the right child, or whatever it is for the next node in the list. However, we won't really be able to check if this is a left or a right node necessarily at the tail of our list, our linked list. That's a tricky thing that we'll have to ponder, consider. I get this feeling like if I coded this up, I would have to do quite a bit of testing to make sure that I did this correctly. But this actually seems to be a feasible algorithm to maintain a complete tree, complete binary tree, a complete and balanced binary tree, as we add nodes to it, as we insert nodes into it. Now deleting nodes would be interesting as well. I don't actually know how I could do this, deleting nodes. I think the way to do it to delete nodes is you take the node that you want to delete, and then you would actually do the same shifting algorithm that you just saw, except shift the node that you want to delete into the largest index in the tree. So like, or not the largest index, but the, what do you call that? The leftmost node with the greatest depth. So you would take this node, shift it with this node, and then delete that, then remove that node, and this would be sort of the same operation where there would be sort of this mutual ancestor node between the two, and then you could perform the same kind of operations. Yeah, I think that's how you could delete a node from a tree in logarithmic time in a self-balancing tree. Now, granted, I think red-black trees are even simpler than all of that, but I like this idea. I mean, this is like a pretty generalizable way to keep your trees balanced. It's probably already been invented. You know, this is probably not a new thing, but this gives you a lot more flexibility algorithmically when you're dealing with data structures than, or more flexibility than I'm used to, in order to maintain certain kinds of trees that are balanced that aren't necessarily search trees, but are just special trees, I guess. I don't even know what kind of a tree you would call this, but it gives you some flexibility if you can get this right. By the way, I still don't really have this algorithm down. I'm not entirely sure. I still don't know. The one part I'm missing is how do you reconcile this left or right tree? I guess you would need to keep a point. What you'd want to do is I'm thinking what you'd want to do is when you find this position that you're going to add the node to, you would demark whether or not it's a left child or a right child, and then somehow you need to contain that information. I guess what you could do is like this linked list. It's not necessarily a linked list of nodes. It's a linked list of nodes and with a little bit of meta information. So it could be a struct with a node pointer and then a bit of meta information. That meta information will say if it's a null pointer, the node is a null pointer, then you could tell whether or not it's a left child or a right child, right? And your linked list could be that, and then you could still do the same operations. But once you get to this point where you're checking, okay, for 3, basically when you're moving 3, what's the relationship between 4 and the next thing in the linked list? Well, that next thing in the linked list is actually a null pointer, and we know it's a left child. So now we can, for 3, we can figure out, okay, it's actually a left child. We want 4 to become the left child of 3, and the right child of 3 is then stays the same. Or excuse me, 4 becomes the left child of 3. The right child of 3 then becomes the right child of 4. So 3 is replacing 4. So everything that's true about 4 should become true about 3, except for the key things that we know we're going to change. So the parent of 3 is still 5. That doesn't change, right? Because 5, we already figured that out. That 5 is going to be sort of, yeah. We already know that doesn't change for 3. That's the same. The right child for 3 should become the right child of 4. The left child for 3 becomes 4. Because the left child, the next value is the left child of 4. How do we figure out all 3 different point values of the left child, right child, and left child, right child, and parent, right? So for 6, the parent is the next node. So the left child and right child should stay the same. And it's the parent is the next node, and we're going to replace that node with 6. So the parent for 6, it's now the question is, that's still going to be 7? What's the parent for 6? What's the left node for 6? What's the right node for 6? Well, you're replacing a parent, and the node above that parent is also a parent. Okay. What does that tell you? So there's like a lot of different cases to go over. There are a lot of different cases to look at, to think about, to go over. So and hopefully my volume isn't too low here. And 7 is a left subtree of 8. All right, the relationship between the 2 next nodes. So 6 is going to replace 7. 6 has got to be the left subtree of 7 because 7 is left subtree of 8. The right subtree of 7, which doesn't get touched, is going to become the right subtree of 6, right? And the parent of 7, I guess, stays the same. So we didn't get into how what we're going to do for 7, but 6, it's replacing a parent, or it's shifting up to become where 7 was. So 7's right subtree should become 6. 6 should be a left subtree of 7. It's so confusing. I don't know, man. In this case, 6, the parent stays 7. The right subtree of 7 becomes the right subtree of 6. The left subtree of 6 was the left subtree of 7, so 6 stays the left subtree of 7. Well, no. We're trying to figure out the subtree for 6. The left and right subtrees for 6 and the parent for 6. We're trying to figure out those 3 things. So the left subtree stays the same. The right subtree becomes, because 6 is the left subtree of 7, it doesn't change. But the right subtree then of 7 needs to become 6's right subtree. And 7's right subtree becomes 6's right subtree. 7 is the parent of 6, so that doesn't change. Right, so 7 stays the parent of 6, left subtree of 6 stays the same, right subtree of 6 becomes the right subtree of 7, which in this case 7 doesn't have a right subtree. Okay, fair enough. I think that makes sense. Then what do we do for 7? 7 is going to move up to where 8 was. The left subtree of 7 is what? Well, 8 is the parent of 7. The left subtree of 8 is 7. So I would say the left subtree of 7 shouldn't change. The right subtree, however, since the left subtree of 7 is not going to change because it is the left subtree of 8, the right subtree of 8 then needs to become the right subtree of 7. And the parent of 8, 8's still going to be the parent since, and 8's still going to be the parent of 7. Since 8 was a parent of 7, it's going to stay the parent of 7. So 7, I guess that makes sense too. How do we know that? Yeah, I guess because 7 is the left subtree of 8. So it stays. Now it stays a left. Its left subtree stays the same. Now 8, on the other hand, 8, it's going to replace a parent, which is 5. And what about its left, right, and parent? How do we change these things? So the left subtree of 8 changes. Left subtree of so why did the left subtree of 7 not change? Because seven is left subtree of 8. 8 is a right subtree of 5. 7 is left subtree of 8. See, that's a little confusing. So 8's left subtree does change from 7. 7 becomes its right subtree, and 8's left subtree actually becomes 5, the parent. And why is that? So I don't actually know. I don't know how to perform this logic. Before a moment ago, I thought I had it. I thought I understood it, but I'm looking at it again, and I'm thinking, actually, I don't really know. 8's left, right, and parent node pointers, where do they go? So it's going to replace 5. It is the right subtree of 5 already. Excuse me. So that means that the left subtree of 8, so the left subtree of 8 becomes the right subtree of 8. Now, why is that? And 7 becomes the right subtree of 8, and the left subtree of 8 actually becomes 5, and 8's parent becomes the null pointer. Actually, 8 becomes the root. So I think because 5, it depends on 5, right? So 5 is a parent, but 5 is also a root. So that means that 8 is going to become a root, which means 8. So the parent of 5 is the parent of 8. Yeah, basically all of that, you're going to replace that node, right? You're basically swapping with that node. So all of the pointers that aren't in the list all become the same pointers of that node, right? Like in other words, 8 to 5, all the pointers in 5 that aren't so in our list, right? So the next node for 5 is 3, and then the other pointers, one of them points back to 8, and one of them points to the root. So for 8, the pointer that points back to 8 should point back to 7. The pointer that points to 3 and the pointer that points to the root, both of those should become actually, that's confusing too, because 5 is going to replace 3 as well. So the pointer that 5 is replacing, that 8 should now point, that pointer for 8 should point to 5. So 3 is the left node for 5. 8 should now point to 5 on the left child. 8's parent should become 5's parent, and the pointer back to 8, the right node, for 8, that should actually be the previous node's value, which is 7. So 7 becomes the right node of 8. The parent of 5 becomes the parent of 8. And because the next value for 5 is a left child, the left node for 8 should become 5. It's really confusing, but there's like some way of figuring out. There is something to that way to figure out what the 3 pointers should be for each node as you go, and it depends on what's next in the list. So maybe we can refine that. Let me take a break. Actually, let me just kind of take some time. So we're at an hour. Yeah, I did an hour thinking about this. Let's just kind of take a break, and I'm just gonna like hang out for a bit. All right, I think there's a way, like you can take these 2 paths, right? You can take a path to the you have these 2 nodes. You can insert this node, then you can find where you would want this node to be, right, in the complete tree. Which I'm actually not entirely sure how you would find that too, by the way. I think actually each time you insert a node, you basically create a pointer to that position. So you'd have the parent, and then whether or not it's a left child or a right child, right? And then so you would once you've rebalanced, if the parent has 2 children, then you want to find you have some algorithm, I guess, to find the next leftmost empty child, I guess. And we'll think about how to do that. But yeah, suppose we at each insertion we already have this position available, so we don't have to go find it. But if you do that, then once you've inserted your value, inserted your node somewhere, excuse me, then you want to figure out, how do I swap things such that this node moves upwards and the parent of the target moves into that spot, right? And then what you'd want to do, I guess for both of these, you would find a path. You actually kind of want to find the lowest common ancestor, which is an interesting algorithm in and of itself. But for these parent pointers, you could do that in logarithmic time. But you basically find there'd be 2 paths, and then you can build a linked list out of these paths, and you actually want to direct your linked list from the node that you're going to move out to the position that you're moving into. And then once you've built that linked list, of these nodes, which really is struct with a node and a node pointer and a little bit of meta information about the node, because you might have an empty node pointer and you want to know if it's a left child or a right child for the target at the end. And then the algorithm that I was just describing, you should be able to actually shift all these nodes so that way you get into that position. And in theory, you'd be able to keep your tree balanced this way. And you also probably could modify this to work on deletions for self-balancing trees. Now again, all of this is probably unnecessary, by the way. You could probably implement all of this using a red-black tree. However, I think it's a little more complicated with a red-black tree. I don't actually know. But yeah, so the relative order will stay the same though of all these maneuvers. That's kind of the idea of the point. And I want to say, let me think here. What am I missing here? What am I seeing here? Move these nodes. Oh yeah, to find the path, it's not too bad. You just basically create a set of the parents, an unordered set of the parents all the way up, and you create one path all the way to the root, and then the next path up to the root until you keep checking this on the second path. You really don't even have to. Yeah, the second path you would just traverse up the parents until you found a parent that's in your set, and then that's the intersecting node, and then you can walk the path again to build one linked list, and walk the path from the other side to get the other linked list, and then you can reverse one and append it to the other, and then you have your reverse one, append it to the other, and then you have your what's that called? Then you have your reverse one list, append it to the other, and then you have the full path that the algorithm I was just describing. You would want to run that on. And yeah, I think what I was just saying somewhat makes sense, where you basically consider the next node, or the next node, and that node's next node. And so because this node is replacing that next node, you would want to take all of the same characteristics except for a couple key details. One of them is what is the relationship between so there's the next node, and then there's the next node. Where's the next node going? If that's going to be a parent, then you want the next node. If that's a parent, then you want your next node to be a parent. And yeah, because that means that this is going to be a parent also. So whatever parent of this is, is that right? It's confusing. If the next node, if your next node is going to is basically going to replace its parent, that means that this node's parent should be that node, right? Whatever this node is going to become, so that depends on the relationship between it and its next node. That's what we should replace our next node with. So the parent will be taken up by 7. Otherwise, the other things are all the same. So the left node for 7 is 6, or rather, yeah. Let's say the right node for 7 is sort of untouched, so that becomes the right node for 6. The left node for 7 happens to be 6, so I think in that case you don't touch the left node. If the node that is going to be replacing, if that relationship, if that's the left node, you don't touch it, that means the right node becomes the right node of 6. And then the parent node is going to also be 7 because 7's parent is the next node for 7. Hopefully that makes some sense. That's like, it's a little weird, but yeah, you want to look ahead 2 nodes, and that'll let you know what values to pick for the 3 nodes for each node as you go. So how this works for 7, the parent of the next node for 8 and its next node, that's a parent relationship. So this next node 8 should be the parent of 7. 7 is going to replace 8, so we have the other 2 values to consider: the left subtree and the right subtree. The 7 is the left subtree of 8, so we don't touch that. The right subtree, however, should become the right subtree of 7. Right, the right subtree of 8 should become the right subtree of 7. So you do that. Now 8, its next node and its next node are going to have 5 is the parent, however 3 is the left subtree of 5. So the left subtree for 8 is going to be the next node. The parent for 8 is going to be the parent of 5, which is the null pointer. And the right subtree of 5 is actually 8 itself, so the right subtree for 8 should not be modified. Should be left as is. And indeed, well, actually, excuse me, the right subtree of 5 is 8, which means that the previous node for 8, which is 7, should become the right subtree for 8. There we go. That's the logic. Okay, that makes sense. So because the previous node is going to replace the node you're operating on right now, what should become the right subtree for what should become the previous node for 5 is also the previous node for 8. Hopefully that makes some sense. So 5's previous node is the right subtree. That means 8's previous node becomes the right subtree for 8. 5's next node is the left subtree. That means that 8's next node should be the left subtree, which is 5. And the node that's not, the pointer that's not changed becomes the pointer for 8. So 5's parent's not changed. The parent for 8 becomes the root, the null pointer. Okay, that makes so much more sense. I think I get it now. So basically, the previous for the next node, the next pointer and the previous pointer, if it's a left child, right child, or parent, will tell you which nodes should be pointed to by this incoming node. That's the correct way to do it. Yeah, it's really weird, but like it makes sense on some level, but it makes a lot more sense if you describe it that way. So basically, your next node's forward and previous pointers are extremely relevant to what this node should be pointing to. Yeah, there we go. To keep the structure the same. There we go. That makes a lot of sense. And now, despite all of that, I don't actually think this does what we want it to do. Thinking about it, realizing it, actually, yeah, I don't think this does what we want it to do. Not exactly. No, it's fine. No, it does. It's okay. Because the original intention of all of this was that this structure that we have, this in-order traversal, all of these nodes relative to each other stay in the same place, even though you insert a new node and rebalance. So this 1 moves here, this 2 moves here, 3 moves here, 4 moves here. I actually think it does work. I think it's fine. Let me just see. let me just see what happens here with this guy. So this is complete tree with 1, 2, 3, 4, 5, 6, 7, 8, 9, and then a value added here. So we'll do let me create a new picture. Getting closer. Let's do it this way. So I was gonna take a break. Here I am. Here I am, not taking a break. Save. That's fine. Oh, I don't want the same size. Let's do like 30%, or even smaller. Half of that. Just give me a moment here. Excuse me. Gonna give it a subscript of 2. Then we can do. Can take this one and rename that to 1. There we go. So now we don't feel so bad. It's 2. Okay. So now what we want to do is, I said 9 of these, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Now the current position would be of this, and let me actually do what we were doing before, where we have a clean copy that we like, and then we want to modify things. So this is 0, 1, 2, 3, 4, 5, 6, 7, and then this guy is going to be actually between 6 and 7. So this would be, let's try that here. 5, 6, 7, it would be 8. No, excuse me. 5, 6 is here. Now 7 or 8, which one of these comes first? I think 7 is here, 8 is here, 9 is here. Yeah, it's significant. And what I was suggesting was shift these over such that this 4 comes down here. So now you would end up with, let's get this clean copy again. That's why I wanted to do that. Now you have 0, 1, 2, and I'm going to write it in red what these nodes were and what they are now. So this 4 is here, and this 7 is gone. This was 4. This 3 is here. 5 is here. 8 is here. 6 is here. 7 is here. And these are, and we're right in green, when you read the in-order traversal, what you get 0, 1, 2, 5 comes next. This comes 4. 4. You get actually, this actually comes next. 3, I don't know, 5 rather. 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. And before we had, no, that's wrong. That's 11 nodes. 0, 1, 2. This is 3, 4, 5, 6, 7, 8, 9. Yeah, so I think I'm actually just wrong about with this idea. This will keep the tree balanced, but it won't keep the same order that we wanted before. And the reason for that is this 7, which would appear between 6 and 8, now appears to the left of 6. 8, yeah. Yeah. Whereas before it was to the right. So this is wrong. This is actually wrong. Oh, excuse me. Oh no. Oh no. Oh no. You can't balance it this way. That's upsetting. That's frustrating. Incorrect. Incorrect answer. Oh boy. Oof, man. Oof. Oh. Whoa. Whoa. Right. Before the order we had was, well, it was wrong, the order that we had before. No. No. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, yeah, we want to keep the tree balanced. That was what we were saying. That's why we want to modify this. Excuse me. Excuse me. And what happened? Now we have 0, 1, 2. This 5. 4, 3, 8, 7, 6. Excuse me. 0, 1, 2, 5, 4, 3, 8, 7, 6, 9. Oh. So the problem with this is that these are not in the right relative orders. This is not in the right relative order. We want to keep the same order, but also balance the tree. That's the intention. So actually, we're not correct. We're not correct. Somehow we swapped 3 and 5, and 6 and 8. Not intentional. Not what we wanted. So, I mean, you could just literally swap those two elements. Yeah, you could just swap the two directly. However, excuse me, how many of these mistakes do we end up with? That's the question. If there's only a handful of these that we end up with, then these swaps that we need to do at the end, then it's not a big deal. It's still logarithmic time complexity. However, if there are a lot of those, and by the way, figuring out what are those errors that need to be swapped out, that might be a non-trivial thing. That is really interesting, though, that the 3 and the 5 and the 6 and the 8 are just need to be swapped. It's kind of weird. Kind of wouldn't expect that. I don't know why that would be. Whoa. I think it's because things that were left children become right children. I think that's why you end up with that kind of a weird situation. If a node had swapped from a left child to a right child, then you might very well just want to swap those two nodes. So that way actually that's not bad. That's not a bad idea. Maybe that's exactly what you're supposed to do, because that would handle that, right? Where the 6 and the 8, what was a left child, if that becomes a right child, then actually just swap those two nodes completely at the end. And so you can kind of just keep track of, like, you can create like basically a list of node swaps that you want to perform of these node pointers, and then walk through the list, and the list can't be more than logarithmic size. So yeah, so you have 6 and 8 is one such position where 6 was a left child of 8 and now it became a right child of 8. And then 5 and 3 is a left child of 5, but 3 becomes a right child of 5 when 5 gets pushed down. And so you'd swap 3 and 5, which is, yeah, exactly correct. And 6, 8, 3, 5. 8 is a right child of 5 and becomes a parent of 5. Apparently that doesn't make a difference. It doesn't matter. It's still to the right. Yeah, it's still to the right. If it's a parent, it's still to the right. Well, it would matter if 5 became a right subtree of 8 rather than a left subtree of 8. 5 being to the left, 5 being a parent of 8 in this particular context seems to be okay. Yeah, it kind of does matter. Like, well, we're kind of always going to the left, so we don't necessarily care that much about the root node. Almost doesn't matter in all cases because we're typically going to go from right to left. Almost necessarily going to go from right to left. There are cases where we go left to right, actually. No, if the node is here and you want to go to this spot and you're going left to right, like this way. Excuse me. So you do want to make sure, like, it depends on where the position is in the in order traversal and this node. If those two positions are swapping with each other, then you definitely want to perform a swap on those nodes. I think that's tricky is to maintain. You have to maintain the correct order. The thing I'm wondering though is maybe these swaps get kind of complicated because like we're only looking at a couple levels here of depth. I want to say when the depth gets larger, then those swaps actually can get more complicated in terms of what they affect. because of how far away the nodes can be in terms of value, and just a simple swap might really throw things off. If that makes sense, because like you see, there's one node in between, but maybe there's like a whole bunch of nodes that could be between these two, and if you swap them, I don't know. I guess it doesn't matter. I guess it's fine. You just want to maintain the relative order, which does stay the same, right? Everything to the right of these two is still to the right, and the things that are to the left are still to the left. It really is only just between these two nodes where it matters. I want to say something like that. I want to say like this tree stays the same, as long as that tree is correct. This left subtree. But yeah, I guess you have to do an analysis of like, it's clearly if a left and right position swap happened, then you do want to swap these things. But if a like a left child becomes a right child, yeah, that's, you want to swap. But if to keep this node on the right side, but if a right child becomes a parent, then you have to make sure that this next node became a left child. If it became a right child, so if this became a parent and this became its right child, I don't think that would make a lot of sense, but yeah, it could happen actually if you're going up this way, right? So this is a left child, it becomes the parent, and then this is not the right child. I think in every case, that's actually not a problem, because in every case it sort of shifts to the correct position, where this is moving to the right where it was to the right, and this is moving to the left where it was to the left. So I don't think that's an issue when you're dealing with becoming a parent. But I think it does matter if you're dealing with left and right children. So this left child became 5's right child, so you'd want to swap those two. And then 4 was the right child of 3, and now it became the left child of 3, which actually doesn't matter, as it turns out. Which is kind of interesting. Yeah, that's the only case I think where it doesn't matter, is when you're dealing with the last node. Because the last node is not swapping with anything, right? Like yeah. Being a right child doesn't really matter. It does matter if you moved it over here, though. In fact, let's think about that. What would happen there if you did? Well, no, actually. Yeah, if you did, no, that never happens. You add a node here, and that would just be done. Huh. I don't know. I don't know if it's that simple. It feels like it might be more complicated than that. But this is like a really complicated algorithm to do this. It would be fast if I can get it right, but I don't think I can get it right. Like I still need to get this linked list moving algorithm, get that right, have that make sense, which is what I was describing for it before. It depends on the previous node, the next node's previous and next node. That determines which pointers your node's going to have, which ones change, which ones don't change. And then you also want to have, and you have to have that meta information that I was describing before, and then you also need to do some linked list manipulation, where firstly you have to find the least common ancestor, which we're going to have parents in our tree, so that should be relatively straightforward. But there's a small algorithm to do. There's an algorithm to do that, and then you're going to have a least common ancestor, then you build a linked list right between these two paths, so you get these two different paths, and build a linked list and reverse one of the linked lists and combine the linked list to get the full path. Then you perform that algorithm that I was describing to shift all these nodes into their right positions. And by the way, once you've finished, and then you have a swapping you want to do, which by the way, you want to actually somehow determine what the next value is going to be, also in logarithmic time, so that way you're prepared for the next call to insert. We'll have to figure that one out. But then you do all these swaps, which I'm hoping what I just described will actually resolve those issues. I don't actually know. I get this feeling like if you make the tree large enough, then you can run into situations where simply swapping those nodes does not resolve your problem. Which I could be wrong. I don't actually know. I think it'll work, but I probably would want to run through some test cases and also think about like a proof to prove that it's correct. So you perform all the swaps as described. You push all those pairs into a vector and then just run through the vector. It's logarithmic, so and perform all the swaps. And then you also want to do one more thing, which is right, the balancing. Yeah. So you need to have this, not the balancing, but the next value, the next node, which basically is going to be your last node, where you want the parent, and you want, if it's a left child, or the right child, because it's going to be a null pointer. So pretty much that last node, it's either going to be its parent's right child, or it's going to be the parent's right child, or it's going to be its parent's right child, or if you don't have a parent, that means you're going to the right subtree, then it's going to be the root's left child, I think. It's got to go down the left subtrees. And see, that's a challenging thing, isn't it? I guess you would want to check if you're not a right child, you want to check, is this subtree full on the parent? If it is, you have the left and right child, then you go to the next subtree. And I think we were saying before, we would want to do this interval thing in the first place to figure out where you'd want to insert a node. You want to keep track of, in each subtree, each node, you want to keep track of the number of children. So if that's full as well, so I guess you would have a depth too involved, so you can quickly determine whether or not it's a full tree. And which, by the way, we also, with all this maneuvering and whatnot, we would want to modify the children of each node when you perform these swaps. When you move the pointers around, it actually changes those values too. So I also want to think about that too. We'll kind of have to somewhat worry about that as well. Oh man, it's getting complicated, huh? It's getting complicated. Yeah, a little bit complicated. I don't know how easy that would be either. Just by the way. Excuse me. Oh, I have no idea. After you move everything around, what are the relative subtree counts? Oh boy. Oh boy. Oh no. Yeah, it's a little bit involved, huh? That is a little bit involved, huh? Oh no. Oh no. Uh-oh. Maybe we should just go check out the red-black trees. Maybe we should just go check out the red-black trees. Oh boy. I don't actually know how to handle the interval stuff. The integer, the number of. Excuse me, the number of sub nodes. Yeah, the number of nodes in each subtree. Because actually, because we're shifting these nodes around, that's actually going to change for each node. So the ones that are moving up, they're going to take on the value of the next nodes. The parent node is going to just take the value of the parent node, and but the ones that are moving downwards, I want to say you just take on the value of each node, previous node. So this node's previous value, when these get shifted up, would be, this was 0, stays, it's the previous, oh no, it's the, I want to say it's the previous, so, no, well this one stays 0. This 6 was a 1, it takes on 8s, it takes on the next, so 8 was 1, 2, 3, 6 is a 1, so 7. Well, the first one doesn't change. That stays a 0. 6 becomes 1, 2, 3, 8's value. 8 takes on 5s. 5 takes on 3s. 3 takes on 4s. And 4 takes on 0. Which of these 4 was always 0. But I want to say 3 actually gets a +1 somewhere in there too. No, 3's fine. I want to say the only one that changes considerably is the root. When that shifts into another tree, that increases by 1. So 5 will take the next one +1, and everything else just takes what's in front. So 3 takes on 0. I want to say it takes on what's in front +1. I want to say if you're moving to children, then you add 1 with the thing you take on. And if you're moving up to parents, then I guess you would subtract 1. Because yeah, you're actually moving out of this subtree into another subtree. Unless you're moving to the root node, in which case you just take on the whole thing. So going up the tree, you subtract 1, down the tree, you add 1, and you take on the previous value. So for 7, you take on 6 minus 1, which is 0. 6 would take on 8, which is 1, 2, 3, minus 1 gives you 2, which is wrong. Wait, what? Why? What? What's going on? So I don't get it, man. Excuse me. Oh no, I'm sorry. I was right. 8 is 4. Yeah, no, I was right. 8 has 4. So 6 would take on 4 minus 1, which is 3. And then 8 takes on 5, which is the root node, so you don't add or subtract. 5 takes on 3, which you add 1. 3 takes on 4, and you add 1, and 4 moves to this position, which is actually a leaf. Which, in that case, actually you don't add 1, I think, instead of being 0, because there's no nodes there. There's nothing to swap 4 with. So I guess 4 you just don't change. Yeah, leaf node just stays leaf node. Yeah, okay. A little confusing, but yeah, you also have that to modify too with your algorithm. I think that's fine. I think that works. So then you have the swaps, and you have the interval, or not the interval, the index, and you have or the sum, swap, the sum, the moving everything, and then finally you want to find this next. So, excuse me. Basically, it's the leftmost node. It's the rightmost position of the lowest level of a tree. Yeah, the greatest depth of the tree. At the level of the greatest depth of the tree, it's the rightmost such node. And so in logarithmic time, you want to find that. So basically, you can, once you get a next child, you could say, does the parent have a right child? If it does, then that's it. If this was a right child, this parent is full, meaning it has 3 nodes, depending on the depth, so how far you go. So you're at sort of 0 depth here. Go up 1 parent, check how many nodes you've got. If you have 3, then you want to go up another parent. If you've got, I think it's just 2 squared. It's 2 times the depth, 2 raised to the power of the depth plus 1, or we'll just say the number of hops. We'll just say hops upwards. 2 times the number of hops upward minus 1. So if you have 1, 2, 3, 4, 5, 6, 7, right? So 8 minus 1 is 7. If you have 7 nodes there, that means that's full. You got to go to the next parent. If that's full, then that means you got to start a new depth. You got to just go all the way to the bottom left. If the whole tree is full, start a new depth all the way to the bottom left. If it's not full, you keep going up to the next subtree until you find a subtree that's not full, or the next parent until you find a subtree that's not full. And then what you want to do is take the leftmost node of the right subtree, or yeah, then you would start searching the right subtree and say, is the left subtree full? If it is, look at the right subtree. If the left subtree is full, right subtree. If the left subtree is not full, so in this instance, this left subtree is not full, take the leftmost node. Actually, no, you want to recurse, really. You'd actually want to recurse on the 2 children. So you would say, is the left subtree full? If it is, right subtree. And do that. So then maybe let's say there's some nodes here. And if the left subtree is full and there's a right null pointer, then that's the one you want. So if there was something here, this left subtree would be full. You take that right tree. If the left subtree is full and there's a right subtree, you'd operate on that right subtree. If there is no right subtree, that's the position you want. If the left subtree has nothing, it doesn't exist, that's the one you want. If it does exist, check if it's full. If it's not full, recurse there. And that's how you iterate from the root node that you found that's not full. But first you've got to move upwards to find a root node that's not full. And then you iterate downwards recursively as described. That should work. That would work too. So we can do all these different pieces. There's a lot of different pieces involved here as described. Kind of just went through it all. But I still haven't proved that this works. The thing that I haven't proven is that if the swapping does what we want it to do. If all those pieces work, if I can get them all to work and prove that they're all correct in all cases, then we have solved this problem, right? Because then we can insert, move to keep the tree balanced, to perform all those operations, insert again, move to keep it balanced, do that over and over again. Also, I think the deletions too, if we wanted this to support deletions, we could also do that by, we would also have to modify the updates to the counts on each node So that is like insanely complicated just because it has so many different pieces involved. Now, all of those pieces I think are doable, and I think you could prove some of these things to work. Also, haven't reversed the linked list in a while, so there's that too. It's kind of funny. But yeah, definitely an interesting situation here. Excuse me. Excuse me. Excuse me. One more issue, by the way, is when we're doing this thing where we reverse one of the linked lists, the target that we're looking for, really both paths are going to go upwards. So the interesting thing about the target is there's some meta information to figure out whether or not it's a left child or a right child. But the initial path, we're only going to know the parents. So actually, when you push that into the linked list, it's going to be the head of the linked list, and we can check the parent node to see if it's a left or a right subtree, and decide there, right then and there. And then when we reverse our list, we don't need to think about that. That's kind of just a minor point, but yeah, you would do that kind of first for the target. So you create those two paths, and then where they meet, you can then reverse the one with the target in it. I think it's the one with the target that you would reverse and append that to the one that's the, I guess, inserted values is the head. Super interesting. Yeah, I think all of those things that I described, if you can get it to work, then you're in good shape. Then you're in good shape. Yeah. I think the swap stuff, I don't have a proof for that to be correct. It's correct in this instance, but I don't think it's, I think it's the one thing that I can't prove immediately that it works. Everything else should be fine. Everything else makes sense. But that's the one thing that doesn't really make sense, or is not obvious whether or not it's true. Because I can't really easily test on like very large test cases. All I can say is like, you're shifting these nodes upwards and around, and necessarily it's got to be between two subtrees of the larger tree, whether it includes the whole tree or not. There is like a least common ancestor that acts as like a root node, and so when you swap things around, I want to say that the relative order is the same. Like everything in the tree, the relative orders are supposed to stay the same. It's just how are these nodes relative to each other? Well, moving things on the right side subtree up and over to the left subtree, for the most part, everything on the right side will stay to the right. What about things on the left side? Yeah. Moving from a right subtree up to be a parent, that's still to the right. Moving from a left subtree up to a parent, the things on the left of that will still be to the left. Would it end up being to the right of some things? Yeah, it could end up being a left subtree up to a parent on a right. Yeah, that a left subtree up to a parent, you could end up being from a left subtree up to a parent, you could end up in a position where the right subtree of that node, which is supposed to be larger, now ends up being smaller. Yeah. And so you might actually want to swap that value with the value you just moved into, or with the previous value. Yeah. A left subtree becoming a parent. You probably want to swap. If there are any children. Actually, in this case, it's the right subtree, so it doesn't matter. That's the thing, you don't necessarily know what the direction is. So it kind of depends on the direction, but if the direction is from the right subtree, because you're transferring one node from a right subtree to a left subtree. In which case, all of the nodes that are going up, you want to follow that rule, where if the left subtree node becomes a parent, then you want to swap. Right subtree node doesn't really matter. So here is the left subtree node becomes a parent. We want to swap those two. And this right subtree node becomes a parent is not an issue. And then on the other side, there are some issues with regard to parents becoming children and where they end up going. But that depends on the direction. So if we're actually going the other way, which you can tell from the indices of the values that are what the index of the target is and what the index of the target versus the index of the inserted node. And I don't know how you would figure that out, quite frankly. But basically, if you're moving to the right, then there's a different rule for the parents. If you're moving to the left, then the rule, I think we went over it, is if a left subtree becomes a parent, then you want to do a swap to keep everything consistent. The children are a little bit different. 3 to 4. Yeah, we don't have too many nodes to look at, but I want to say 3 being a parent is always going to be, so a parent going to become a right child is fine, but a parent becoming a left child is not necessarily fine, right? So if 3 comes down here, that 1 might become a left child, but this 2, so actually just this 3 being pushed where this 1 is, this 2 is now greater than that 3, right? And that messes up so yeah, parent becoming a left child is an issue, and a child becoming a right parent is an issue from right to left. So when this parent becomes a left child, that's when, which is actually what's happening here, this becomes a left child, and I think that's why we swap 3 and 5. You actually could just swap those two, right? And that should be consistent. Now, not necessarily, right? Because now 5 is before 3. No. Yeah, you push 5 becomes a left child, and 3 either goes to the left or to the right. Actually, swapping them is not really necessarily what you want to do either, by the way, because 5 is the parent of the left child. The issue is this 3 isn't necessarily going to be to the right of 5. This 3 could go further to the left to 1. Well, actually, if 3 goes to the left, that's not an issue. However, if you do that, then this 4 is a problem, right? So if 3 goes to the left, you actually do want to swap 5 and 3. Do you? No, you don't. Yeah, I actually don't know. I don't think this will work. There's too many cases to consider. when you're shifting down to the left. I think up from the right makes some sense, but down to the left is really confusing because basically when you shift 5 to the left, everything in this right subtree is supposed to come before 5. And so it seems like you need to swap 5 with with the right child. So then 5 is the head of this subtree, and I don't know where 3 went, but then so 5 is the head of this subtree, and 3 is nowhere to be found. It just so happens in this case, when you push down this 5, 4, it's still to the right, but if you swap 5 and 3, then 5 ends up being down here. I guess you would end up swapping 5 with this node no matter what, but basically, to keep everything consistent. Yeah, I guess that makes sense. And then, so if 3 was going to be pushed down to 1, you would swap 3 with 2. Yeah. And assuming 1 is pushed down here to where 1 is, or 0 is, you'd have 1, 3, 2, so you'd swap 2 with 3, so 1, 2, 3, and continue. I think that makes sense. Basically, yeah, if you push, if you're swapping with the left, if you're shifting to a left child, then you actually want to swap with the right child after shifting. Interesting. Interesting. I think that's it though, because if you swap with the right child, or you push down to a right child, then, well, actually after the swap doesn't matter, but yeah, if you push down to a right child, then kind of messes things up, right? Because the swap that we were thinking about doing doesn't really make sense, because now we're looking at swapping 5 and 3, but then let's just say you don't do anything if you move to a right child, but then you have this 4 is moving to a left child, and you're thinking, well, what do you swap that with, right? We'd say the right afterwards, the right subtree. But if there's no right subtree, then I think you just leave it. But that's kind of the thing. If we push 5 down and then swap 3 and 5, that doesn't make sense either. It doesn't, because 4 still ends up being to the right of 5 or the left of 5. Oh no, no. In the in-order traversal, it's supposed to be to the left here. So we swap 3 and 5. It's not a big deal. That's so confusing. Still don't think that logic works in all cases. Still feels wrong. And obviously, what we just described would go in other directions, the sort of mirrored directions if you're going from left subtree to the right subtree. Oh man, this is quite the algorithm to self-balance this tree. I still think it's possible, but it's like, man, that's a lot of thinking and describing and working on it. I think probably better would be to just try to look at how are other self-balanced trees balanced, and then just implement that. And don't go through all this hassle. That was a lot of describing and thinking. How many hours are we in here? Over 2 hours of just pondering this here. It's really a lot. It's really a lot. It's maybe a little bit too much. I need a break. I should take a break. I don't know, man. It's not adding up. All these pieces. It's not adding up. It doesn't add up. It's quite the challenge. Quite the challenge. Yeah, I definitely think. I think if I kept going, I might. No, it's just the logic for this. The swapping is the only part that's really tripping me up now. I don't think it makes sense. I don't think it'll work. I don't think you could prove that it works. The logic I described. I think I'm better off trying to. Excuse me. I think I'm better off trying to. Trying to look at the other kinds of self-balancing trees. This is really interesting though, because it seems so close. It seems so close. I think I would just need to spend a little more time on the logic for how the nodes, when they're when you're shifting all these nodes, how to keep them in the right position. I'd probably need to run a bunch of test cases too to get an idea of like where do these nodes actually end up? Like how far away in the in-order traversal are we? Is it a matter of just a few swaps, or is it more complicated than that? And go through some different test cases. Because just from a few things I thought about, it seems like it could be just a few things, but I think realistically it's going to be a lot more complicated than that. I think something like that. I think it's actually not that easy to do that, perform those swaps properly. So I don't think it'll be that easy to do, and so we won't have logarithmic time, and all falls apart. So let me try that. There must be a better way to do this with just what's already out there with regard to self-balancing trees. So I'll look into that. But this is definitely. It feels like we're really close. I want to say it's likely that we're not as close as we think. It might be actually not possible to do this the way I want to. But man, did we get close? It seemed like we got close. Probably didn't get close at all, but I don't really know. I have to kind of go through it some more, come up with a way to prove that this works, and then code it up, try it out, see how it goes. Oh, excuse me. I think what I prefer, there's like two options, right? To pursue that, continue pursuing that. But the other option is to at least two possibilities, and the other possibility is to look at already known self-balancing binary trees, and then try to implement a version of that implements the interval insertion that we're looking for. Try to borrow some concepts from that. Thinking red-black trees. Maybe we can do it, maybe not. I don't know. I'd have to look into it some more. So we'll probably have some time where I'll probably take some more time later. Maybe not today. I'll just take a break today. Probably, I don't know what I'm going to want to do the rest of today. But take a look at red-black trees next, I think. And in theory, I could borrow some concepts from red-black trees to implement a simpler way to keep this tree balanced, keep my tree balanced. If I can't do that, I'll be sad. But if I can, that'd be great. That would be fantastic. All right, let me go. Thank you again for watching. I will talk to you soon. Have a good rest of your day.